In this module, we're going to be talking about joining data frames. Let's start off by doing our normal imports. We're going to be importing Numpy as NP and Pandas as PD. And let's make two data frames, df1, pd.dataframe. And it's going to have a column called name. Our names will be John, George, Ringo. It's going to have another column called color. And the values in that will be blue, blue, and purple. And we're going to have one more data frame called df2. And it's going to have Paul, George, and Ringo. And it will have a column called car color. We'll have red, blue, and np.nan. We're also going to specify an index for this last guy, and his index will be 312. Just inspect our data frames here. Here's df1, and here's df2. So if we have our data frames here, we can concatenate the rows. Let's look at how we would do that. There's a built-in function in Pandas called Concat, and I pass in a list of data frames that I want to concatenate together. So I will concatenate a list of df1 and df2. When I call concat, it says, do any of the columns match? If they do, line those up. Otherwise, put in nans for the other column. Note that if I run this and I pass in the data frames instead of being in a list of data frames, I'll get an error. So don't do that. By default, this PD concat, we look at the documentation here, he's going to do an outer join here. And if I want to do a different kind of join, I can say join equals inner instead of outer. And in that case, I only get the columns that are in both of them, which is name. That may or may not be what you want. Another option that we can do is called verify integrity here. Verify integrity says check whether the concatenated access contains duplicates. This can be expensive relative to the actual data concatenation. Let's just verify that. And it returns a value error. We have overlapping values 1 and 2 in our index. And we can see that indeed 1 and 2 are in both. And so the integrity complains about that. If that is an issue, if your indexes are important and verify integrity returns that error, you can do something like this where you can say ignore index equals true. And if you pass in that parameter, ignore index equals true, then it's going to just generate new index for you. In this case, it does monotonically increasing index from 0 up to 5. That's how you concatenate two data frames together. You just pass them into the concat function in Pandas. We've just seen how to concatenate rows. Let's look at how we would concatenate columns. We can use that same pd.concat function. We'll pass in df1 and df2, my two data frames. Instead of concatenating on rows, which happens to be axis 0, we can say we want to concatenate on the column axis, axis 1. And if we do that, it lines up the two data frames and puts them next to each other instead of on top of each other. We can see that now we have duplicate columns here. We have name, it's duplicated twice, but we do see that we have alignment on the name column. So George aligns with George over here and Ringo aligns with Ringo. The John name in df1 did not have one in df2, so he gets nans in there, and similarly for Paul in df2. Let's just dive into concatenating columns a little bit more. I can do very similar stuff to what I did with my concatenating rows. I can say join equals inner, and that will say the only names that overlapped were George and Ringo, so let's keep them. I can also say verify integrity equals true, and that's going to give me an error because name overlaps in both of those. So if I have columns that are duplicates and I don't want duplicate columns for some reason, I want them to count up starting at 0, I can do ignore index equals true, and that gives me new column values 0 up to 3. So that's how we tack on columns if we want to by joining them with the concat function. The nice thing about this is that it aligns the columns that line up and will join them doing the right thing there. Let's look at how we would do joins similar to database joins in Pandas. on the data frame, we have a method that is called merge, not join, and that's what we're going to use. So I'm going to merge data frame 1 with data frame 2, and if I do that, I get something like this. George and Ringo are in both data frames, so it's going to do a nice little merge and add those other columns in there, color and car color. I can specify the type of join I want to do. I can say how is equal to an inner join, and that happens to be the default. I can also put in another parameter here called indicator. If I say indicator equals true, that puts in this nice little column called underscore merge that says that George and Ringo happen to be in both columns. And that's correct because we're doing an inner join, and so the name should be in both for an inner join to work. By default, the merge method tries to find the column names that overlap and use those to merge on. If you don't have column names that overlap, you can specify your own, or say I want to merge on color and car color rather than name. I can say left on color and right on car color, and that gives me this guy where it's merged where the colors are the same. In this case, John had a blue color and George had a blue car, and George had blue in df1 and he had a blue car in df2. So if that's what you want to do, you can do that as well. Another parameter that you can put in there is you can say suffixes. Suffixes equals, we're going to pass in a tuple, and we'll say fav underscore car. Now it's going to say we merged on car and car color, and name underscore fav came from df1 and name underscore car came from df2. So those suffixes allow you to tack on suffixes to each of the data frames that you're joining together. So this module has talked about how we merge two data frames. Specifically, this is talked about inner joins, similar to an inner join in a database table. And that's the default type of merge that happens when you call merge. We've talked about inner joins. Let's look at outer joins. Very similar to inner joins. The syntax looks the same, except we changed the how parameter. So I'm going to call the merge method. That is not the join method. You want to call merge to do a database join in Pandas. And I'll say how is equal to an outer join. What that does is it says I'm going to merge these based on the common column. Common column in this case is name. John did not appear in df2, so we're going to put in car color is not a number. And Paul did not appear in df1, so we're going to put not a number. Let's just look over the other parameter options and see what they do. If I say indicator is true, that gives me this underscore merge column, and it tells me that John was only in df1 and Paul was in right or in df2. Can be useful if you're debugging these joins to see how they work. And again, by default, when you join, it looks at the columns, and the columns that have the same name, we're going to use those. If you want to join on other columns specific to the data frame, I can say I want to join left on color and right on car color. So in this case, I'm merging based on color and car color. If we look at the results here, we see in row 0, color is blue, name X is John, car color is blue, and name Y is George. So the blue for John corresponds only with George in df2. In row index 1, we see the blue George that corresponds with both. Purple Ringo, he doesn't match up with df2. And we see that his underscore merge says he was only in the left. We see that Paul was also only in the right, and we see that Ringo was also only in the right. That's how we do an outer join. The thing to be careful of here is you see that in row 0, John and George are getting linked up. And that may or may not be what you want to do. So you got to be careful when you're doing an outer join to make sure that you're getting what you really want to get there. One other option that you might want to do is you might want to merge based on the index rather than the column. So you can say, I want to merge on left index and right index is true. And we can see that df1 had an index 0, but df2 did not have index 0. So that's a left only. 1 and 2 were in both, and 3 was only in the right or df2. This is a merge based on the index columns rather than the column names that overlap. You can also see that by default, Pandas is putting in _x and _y for you because those names overlap. You can change the suffixes if you want to. So fave color and car. And now instead of _x and _y, it says _fave and _car. So that's how we do outer joins in Pandas. Again, the main things to be aware of is that by default, it's going to look at the columns that have the same name and join based on those. If we want to override that, then we can say left on and right on to tell it what columns to merge on. We can add the indicator parameter to help us debug a little bit. And remember, we want to call the merge method merge is join, don't call the join method. Let's look at how we do left joins in Pandas. df1.merge, I'm going to merge with df2, and now I need to say how is equal to a left join. Very similar to our other joins we've been looking at, but a left join takes everything that was in the left data frame or in df1 and aligns it with df2 if df2 exists. If df2 doesn't exist, it's going to fill it in with not a numbers there. So we see that John and Ringo were both in df1 but not in df2, so car color gets filled in with nan there. If we want to debug it a little bit, we can put in our indicator here, indicator equals true. That gives us the nice little _merge column. Now, the interesting thing about this is I previously said that George was the only guy in both df1 and df2, and that's not the case. Ringo is in df2, and the merge tells us that he was in df2. From that, we can assume that his car color in df2 was not a number or empty. So this can be useful in helping you debug and figure out what's going on with these merges and where your values are coming from. And again, if we want to, we can do, say, I want to merge left on color and right on car color. So you want to be specific about what you're merging rather than having the same column names. That says, I want you to keep everything that was in the left because we're doing a left join, but I want you to join based on the color column. So the colors that were in the left were blue, blue and purple, and blue lines up with George from df2. And purple does not line up with anything from df2. Another thing that I haven't really shown is that you can do a sort. So I can say df, I want to merge these. I'm going to do a left merge. And here's our left merge. And if I say sort equals true, we can see that this slightly changes it. It's taking what we're merging based on and doing sort based on that. And so the name column is what we're merging on, and rather than being John, George, Ringo, it's alphabetically sorted that to be George, John, and Ringo. So that might be something that you want. Pandas allows you to sort after the fact, so shoving that into the merge operation may be what you want, or you can sort after the fact as well. Because this doesn't allow you to change the direction of the sort, an ascending or a descending, my recommendation would be not to sort inside of this method, but sort after the fact. So we've looked at doing left joins here. These, again, are similar to SQL joins, but we're calling the merge method, and we're saying we want to do a left join by passing in the how parameter as equal to the string left. Let's look at how we do a right join in Pandas. This should be very familiar to you now. We're going to call df1.merge, and we're going to merge it with df2, and we'll say how is equal to right. What right means is I want to keep every row in the right data frame, or df2, and if we merge it with df1, whatever's missing from df1 that doesn't match up, we just put in not a number there. So Paul is in df2, but he's not in df1, so we put in the color of nan for that. And this nice little guy here, indicator is true. We'll just help you debug it a little bit and make sure what you think is going on is what's going on. And indeed, Paul is only in the right side. And just to cover the bases again, I can merge left based on color and right on car color. And we see that the blue car color aligned with John and George from df1, so that there's duplicates in George with name Y. And Paul and Ringo were only in df2, and so they get not a numbers for color and name X. Again, we can do sort and we can merge on index, but that covers the basic joins. So we can do inner joins, outer joins, left joins, and right joins using Pandas. Let's look at joining on indexes in Pandas. We've looked at joining on columns, and we've seen that when we call the merge method, we can also say left index equals true or right index equals true to do a join on the index if we want to. Another way of specifying an index join is to call the join method. The join method in Pandas, df1.join on df2, this throws an error here. Let's look and see what the error says. It says column names overlap, but no suffix specified. So it tried to do a join on the index, and it said I have name in both data frames, so I'm going to complain about that. How we get around that is we can say L suffix equals fave if we want to. And now we see that it has joined based on index. It's done a left join. How is left? We can specify the join types if we want to. We can do a left join or a right join or an inner join or an outer join. Let's just look at those really quickly. How equals outer, there's outer, and it's doing all the index values inner. Only 1 and 2 were in both, and a right. 1, 2, and 3 were in the right index. Join will also allow you to join based on columns, but it's not quite as powerful as merge because you can't specify a left on and a right on. So I would recommend if you're joining or if you want to do a database style join based on columns to actually use the merge method rather than the join method. And the merge method also allows you to merge based on indexes as well. We've looked at the join method, and it offers basically a subset of the functionality of the merge functionality. This module will be discussing how we filter data in data frames. I'm going to import the IO library. I'm using Python 3. In Python 2, the analogous library would be the string IO library. Let's make some data. My data will be triple quoted string, and it's going to be a CSV file that will be pipe delimited. So name, pipe, age, pipe, color. And the first name will be Fred. His age will be 22. His color will be red. Next will be Sally. She's 29. She likes blue. George. He's 24. He has no color. And Fido. He has no age and he likes black. Let's read it into a data frame. If I have data like this, I can read it into a data frame using the read table function. I'm going to pass in that data into what's called a string IO buffer. And I want to say that my separator is a pipe. Let's see if it worked. Lo and behold, I have something that looks like a data frame. Let's look at how we filter now. Filter columns. So I can take my data frame and I can say I just want the name column and the age column, ignore the color column, and I can pass in a list to this index operation here. So I'm saying df index with a list in it. Note that if I just say I want to do an index operation with that in there, I'm going to get an error that says a key error, name and age aren't in there. So you've got to pass in a list if you want to pull out columns. Another thing I can do is I can make a mask, and I can say my mask is going to be take my columns, and since they're strings, I want to apply a string function to them. The string function is starts with. And if the column starts with A, I want the mask to return true, otherwise it will return false. Let's just look at what mask looks like in that case. Name does not start with A, false, age does, and color does not, so false. And I'm going to pass that into the iloc attribute. Iloc allows me to filter rows and columns, so I'm going to keep all my rows. So I'm going to put a colon there, say start from the first row, go to the last row. And then a column, here's a comma here. After my comma comes my column mask. I'm just going to put this mask in here. And I can see that it gives me back everything, but only the columns that start with A. So that's how I can filter columns, simply by specifying those columns or making a mask and passing that into the iloc attribute as an index operation. I want to talk about Boolean arrays. We just saw these in the mask above. A Boolean array is a series that has Boolean values in it. And we can create these Boolean arrays really easily by saying something like this. df.age greater than 25. That gives us back a series that the index is corresponding to what we filtered on, but it has Boolean values in there. Another way I can make this is I can do something like this, where I could say, take the name column and use the stir attribute. This allows me to do string methods on that column. I can say starts with, and maybe F, and I see that index position 0 and 3 start with F. If you don't remember what our data frame looks like, it looks like that. So Fred and Fido start with F. So these are Boolean arrays, and I can make them. We'll see how they're useful for filtering. We've already seen how they're useful for filtering columns, but we'll see how they're useful for filtering rows in the next module. Let's look at filtering rows in data frames. We just saw what Boolean arrays are, and Boolean arrays are one way to filter rows. When I typically create a Boolean array that I'm going to be using as a filter, I like to name it masked just to be explicit about what it will be used for. So here I'm going to make a mask that's going to be similar to what we saw before. On the .stir attribute, I can invoke string methods on that column. So if a string starts with F, I'll return a true for it, and I'll just take that mask and apply it to my data frame. Now I have all of the rows who have a name that starts with F in there. I can make another mask here, mask2, and I'll call that is the age less than 25. And let's apply mask2. That returns a new data frame that says Fred and George both have ages that are less than 25. So that's how we use these masks. We pass them in as index operations, and we can filter with them if they're a Boolean mask. In this section, we're going to look at how to use a function to filter data frames. You can make arbitrarily complex functions and use them to filter data. We have our data frame here that has names, ages, and colors. And say we wanted to make a filter based on whether the age is prime. So there is no built-in function in Pandas to determine whether something is prime, so we're going to have to make our own function. And to make a function that's a filtering function, we call that a predicate function. Predicate function is a function that takes a value as input and returns true or false. In this case, we want our function to return true if a number passed in is prime. So I'll just make a little function called isPrime. It's going to take a value as input and it will return true or false. The basic idea of my function here is I'm going to want to start at 2 and go up to the halfway point of the number. And if any of the numbers from 2 up to the halfway point divide evenly, then it's not a prime number. Otherwise, if I've tried all those, if I've exhausted those, then it is a prime number. I'm going to need a try statement here because of how I'm going to implement it. What I'm going to do is I'm going to get an end number, and I'm going to get the end number by casting the value that was passed in to an integer and dividing it by 2. Now, if I get a nan and not a number in there, then I will get what's called a value error. So I'm going to divide it by 2 and try and add 1 to it. That will give me the end number. Because Python uses the half open interval, when we do the range function, it's going to go up to, but not including the end. So I'm bumping up the number by 1 to make sure I get to that halfway point. So nan's going to throw me a value error, and if that's the case, got a nan, I'll just say return false, not a numbers or not prime. I'll just do my little loop here. For I in range, I'll start at 2, and I'll go to my end. And if the val mod I equals 0, if it divides evenly, then it is not prime. Otherwise, if we've tried everything, then we'll return true, say it is prime. Let's try our predicate function here. Is prime, is 2 prime, it is prime, 3 is also prime, 4 is not prime, that's correct. 5 is, 6 is not. Looks like it's doing good. So let's make a mask by using this predicate function. How I do that is I apply the function to a column. I've got the age column here, and I'm just going to say apply the isPrime method to that, and it gives me what's called a Boolean array out of it. Well, this is a series that has Boolean values in it, and I can use that as a mask. I'll set that to a mask variable, and I'll take that mask and I'll apply it to my data frame. And that gives me all the people who have age values that are prime. So Sally is the only one. I can make these functions do whatever I want. Here would be a very simple one. Here would be a predicate function that a value is less than 25. Return val less than 25. And I can try that out. I can say df.age.apply. LT25 gives me the same Boolean array, and I'll inline that as a filter. I get that value. Be aware when you're doing this, you can apply any predicate function you want, but in this case, we don't need to do that. Pandas has built-in vectorized versions of some of these things, so the less than operator is built in. I can use this directly, so I can say df and take that operation here, df age less than 25, and get the same result. If you can use the functionality that's built in with Pandas, use that. It's typically going to read cleaner and it's going to be faster. So in this section, we looked at how to make predicate functions. A predicate function, again, is a function that takes a value as input and returns a true or false. And to apply a predicate function, you just take a column and call the apply method, passing in that function. In this section, we're going to look at how to use Boolean operations and combine filters and masks with them. Let's make a little mask. This mask will determine whether a name starts with F. There's vectorized string operations to do that. On the column, we can say .str, and off of that, we can call a bunch of string operations. For example, we can say .starts with and F. That will give us a mask. Let's apply that mask. Here's the mask, and we can take that mask and just pop it in, apply it here to our data frame, and we get all the names that start with F. Let's make another mask. I'll call it mask 2, and I'll say df age is the age less than 25. Let's look at mask 2. Okay, we've got some results here. Let's apply it. Fred and George are less than 25. Now we can combine these masks if we want to. There are various ways that we can combine them. We can say apply mask and mask 2. In other words, I want the result where both of those hold true. So this is called the intersection, and we can use this ampersand here. That will tell us where both hold true. If I wanted either one to hold true, I could say mask or mask 2. This is called the union, and we use the pipe operator to do that. And we can see we have names that start with F and also ages that are less than our mask of 25. I'm going to show you something that you need to be aware of. This could be a potential gotcha here. I'm just going to inline my filters here. So name.stir.starts with F, and I'll say df.age less than 25. And here I get Sally in there. Sally does not have a name that starts with F, and the age is not less than 25. That can be a little confusing. Let's try this again and put parentheses around here. What's going on is that the order of operations, the precedence is getting confused, and it's giving us a result that we don't want. So if we put parentheses around our inline masks, we actually get what we want. So the hint here, the takeaway, is that you can combine these guys if you want to. If you're inlining your masks, make sure that you put parentheses around your masks to make sure that the precedence is correct. Otherwise, you might get a result that is confusing or doesn't make sense. In this section, we're going to be talking about dealing with nan or not a number in Pandas. We've seen various data frames and that they can have missing values, and typically that's represented as nan in Pandas. Let's look at our data frame again that we're using here. And we see that we have an age value that's missing, and we also have a color value that's missing. One thing that we can do to quickly inspect which parts are null is we can call the isNull method on a data frame. And it just puts in true or false values whether something's null or not. We can also apply isNull to an individual column or series as well. So we can say df.age is null, and we get a similar result here. We get a series coming out that's a Boolean array. When you have this, you can do some filtering as well if you want to. So I can say df, and I'm going to use df.age is null as a filter, and I can get the row where the age is null. We can also invert that, as we saw previously. If we're doing conditional operations, we can put a tilde in front of it and invert that and find the ages that aren't null. This is useful because often we're doing operations that can't handle null values or a break, especially when we're dealing with third-party operations that are expecting floats or integers and we pass in a null. That can cause problems or just make it not work. Another nice method is one that's called drop NA. So if I call drop NA on a data frame, it's going to return me a new data frame where anything that is empty is missing. This allows you to get a new data frame without any not a numbers in it. Now, one thing to be careful of is that any row that has a not a number in it will be filtered out. So this can be a little harsh, and sometimes you might only care about certain columns not having not a numbers. So in that case, you'd want to be doing the mask operation that we showed above, where you filter based on a single column or combination of columns. Alternatively, the drop NA method has a subset parameter where you can pass in the columns to consider. I'll show you an example of that. I will say subset, and I will only take the age that are null. That needs to be a list. So when I ran that, note that my age that was null for Fido got dropped out, but George, who has a color that is missing, did not get dropped out. We can use this subset parameter to be more careful about what we're filtering. One last thing I want to show you is the fill NA method. This works again on both a data frame and a series. So if I say fill NA with -1, it put in -1 for any not a number values. Sometimes you might want to fill in any null values or missing values with the median or -1 just to indicate that it's missing rather than a not a number. Sometimes external programs can handle -1 or whatnot. But be careful here because note I put in -1 and it put in -1 for color here. And that might not be something that we'd want to do there. We could update the color column by saying df color is equal to df.color fill NA with missing. And if we look at df now, we see that missing is there instead of NA. So that's another option for filling in those missing values. So we've talked a little bit about dealing with missing values here. The key takeaways are the isNull method that works on both data frames and series, drop NA to remove null values, and fill NA to replace them. In this section, we're going to be looking at grouping. Basically, the idea behind grouping is to aggregate columns based on their values and summarize that or return a summary from that. Let's do our imports. I'm going to import Numpy as MP and import Pandas as PD. Let's make a data frame here. This data frame is going to represent students who have taken tests. The first column will be name, and it's going to have a few names in there. Adam, Bob, Dave, Fred. We'll give them an age, assume they're in high school or something. 15, 16, 16, and 15. Here's test 1. On test 1, we got 95, 81, 89, and none. And test 2, we got 80, 82, 84, 88. And let's give them a teacher. Maybe they're in a math class and there's 2 teachers that teach the math class. One might be called Ashby and the other one would be called Jones. Inspect our data frame. There we go. We have names, teachers, ages, and scores on tests. One of the built-in methods in Pandas that's pretty useful is called groupby. I can take a data frame and say I want to group it by teacher, and let's just say describe on the result of that. When I run this operation, Pandas is going to aggregate all my rows by the teacher, and then it's going to take those aggregations. So for example, Adam and Bob both have Ashby, so it's going to treat that as if it were a data frame and invoke the describe method on that data frame, and then it's going to concatenate the results together. So we can see that the average test for Ashby is 88 for test 1 and 81 for test 2, and the average test score for Jones is 89 and 86. Pretty quickly here we can see that maybe Jones is a better teacher or has better students, something like that. So the group by here, we called describe on it, but you can do other things as well. We can say median, and that gives us the median scores for the groups. We can also get fancier here. We can say df group by, and instead of grouping by teacher, maybe I wanted group by teacher and age. On that, I want maybe the median score. Now we have it broken down where we see first we group by the teacher, and then we bracket in the teachers by age, and we get the scores by age. So we can do arbitrarily deep grouping if we want to. We can also call mean on here if we want to and get the mean or the count or the max or the min. All of these are supported in Pandas by grouping. So it allows you to quickly group by some columns and do basically a query to filter out values that are interesting to you. Let's look at grouping a little bit more. We looked at applying various aggregate functions to the result of a group by. When we call group by, we get back a group by object, and that group by object can do various things. As we saw, we can call mean or max or median on it. We can also call apply on it, and apply allows us to apply a function to the individual groupings and then aggregate that. Let's look at how we do that. We can do more complicated things, or we can do things very similar to what we saw above. We can say df.groupby teacher, and let's get the max. So I'm going to say apply, and I want to apply a function, and the function I want to apply is max. Here we see the max age in Ashby is 16, the max name is Bob, the max teacher is Ashby, and the max test scores as well. So this is very similar to just calling max. Because this method apply is what's called a higher order function, because it takes functions as input, note that we're passing the max function in here, we can apply arbitrary functions to our grouping. Here's an example that's pretty trivial. df.groupby. If I just want to see how big my groups are, group by age, and let's apply the len function there. Note that this is giving me back a series, and it's saying that in the age group 15 there's 2, and the age group 16 there's 2. So when our function returns a scalar value, Pandas is going to take the result of that and throw it into a series with the index based on the group name. In this case, we grouped by age, so our index is 15 and 16. And we can do more complicated stuff as well. Maybe we want to get the best teacher in each group by age or whatnot. So I can make a function that says best teacher, and it's going to take a group, and I want to return a data frame, and that data frame is going to have test 1 and test 2, and for test 1 I'm going to determine that. I'm going to have it return a list. It's going to say give me the index of where test 1 was the maximum, and I'm going to take that and I'm going to filter my group based on that, and I'll get the teacher as a result of that. So let's parse through what this is saying again. g.test1.id max is going to look at the test1 series and return the index of the maximum value. And then we're going to use that index to pull off the row using g.loc, and then we're going to get the teacher who taught the student who had the best score. And we'll just copy that and paste that down here for 2. And this will tell us who is the teacher who taught the best score there. Let's apply it now. df.groupby age. And now we're going to apply this best teacher function. Note that we're not calling best teacher here, we're passing it in. So that's a higher order function, one that accepts another function as input. In this case, applies a method, so it's a higher order method. The result that came out of here is a data frame that has the age is equal to 15, and at age 15, Ashby got the best score on test 1, and on test 2, Jones got the best score for age 15. The idea behind the apply method is that you can do arbitrary applications and aggregations. So if we return a scalar value, then it's going to return a series out of it. If we return a data frame, it's going to concatenate those data frames. So we can get series data out of apply, or we can get a data frame out of it. It can be pretty powerful, and you can make your function do whatever you'd like it to do. In this section, we're going to be talking about creating pivot tables. These should be very familiar to people who are power users of Excel. Pivot table allows you to summarize rows in a nice manner. And this is basically an abstraction on top of grouping and allowing us to do grouping a little bit better. Let's look at how we would do that in Pandas. I'm going to make another data frame here called cost. You can think of this as store data. Let's look at this data frame a little bit. It has 4 columns: the cost column, how much an item costs, a day column, when you purchase the item itself, and a store it was purchased from. There's a built-in method on the data frame called pivot that we can use. Pivot allows us to specify what we want to use for the index. So in this case, we'll say, I want to use the index of item, and I want to have columns be the day. Run that in there, and we get a problem here. The problem is, if we use the item, so bacon, as the index, and day, we have a duplicate bacon and day. Let's look at our other data frame really quickly, and we'll see that we don't run into this problem. We had another data frame here with our scores. Let's pivot that. And since we don't have duplicate data, we can see that we can pivot this pretty easily. df.pivot, and I'm going to say index is teacher, columns is name. And we can see it puts the teacher on the left-hand side, and it uses all of the non-name columns, age, test 1, and test 2, and it breaks those up by the names. Since we don't have duplicate names for teachers or students in multiple teachers, we don't have any problem here. But in our cost one, we do. So if you run into an error like that, you can do something like this, or we can say cost.duplicated and say subset equals day and item. And that tells us that at index position 2, we have a duplicate value. Day and item, Monday and bacon is a duplicate from row 0. So that tells us when we have a problem there. In this case, the way to get around this is, rather than using the pivot method, we can use the pivot table method. Pivot table method is similar to pivot. We can say index equals item and columns equals day. But rather than putting the individual items in here, it's doing some aggregation. And the default ag, we can pull up the documentation for this. Default aggregation ag function is numpy.mean, so it's going to take the average of those values. Note that there is no 2.85 for bacon, it's averaging 2.5 and 3.2 for that. So this allows me to quickly make a pivot table in Pandas. Pandas has a few more options that are nice. I can specify the ag function if I want to. So I can say agfunc, and I can specify multiple ones. Maybe I want to say max and length, and I could get something like that. I can also say margins equals true, and that gives me a column on the right called all and a row on the bottom called all that summarizes the results here. In this case, it's taking the mean of all those values. Let's put in a summary column here with ag function for max and len. You can see for each column that it's aggregating, it's going to put in an all column to summarize that, and it has an all row at the bottom to summarize the results of everything. This is a brief introduction to creating pivot tables in Pandas. These are powerful constructs. You can see that these pivot tables are very similar to what we were doing with grouping before. We were saying I want to aggregate based on item, and I want to get the maximum for all of the costs and all of the stores, and I also want to get the length for all of the costs and all the stores. So you could write a function that you could pass into a group by aggregation that would do a similar thing, but this allows you to do it in one line of code. Let's look at one last feature of Pandas that's commonly used with grouping or pivoting, and that's called stacking. Here's my cost data frame again, and let's look at a pivot of that. I'm going to make another data frame called piv, and it's going to be cost pivot table, and I'm going to use index equals item and columns equals day. Let's look at piv here. So here's my pivot table. Now what I can do is I can say pivot, I want to stack my pivot. What stack does is it says take my columns that are subcolumns. Note that I have a cost column and then I have this M column below that for day. And I want you to rotate that subcolumn onto the left-hand side. Explain what that means a little bit more. If you look at piv.columns, you'll see that it's what's called a multi-index, and it has a level for cost, and it has another level called M below that, which is the day. What we're doing is we're saying, when we call stack on the pivot table, it's saying take that lower column M and rotate it down to the left side to make it a row item. Let's look at an example that's a little bit more complicated here. Piv2 equals cost dot pivot table, and I'm going to do the same thing. Index equals item, columns equals day, but I'll say margins is true here. And let's just look at piv2. There we go. So it has two columns here, one for M and one for all. Let's stack that guy and see what happens when we stack him. And we can see that M and all both get rotated to become rows. And so that's the stack operation. If you've got what's called a multi-index for your columns, you can pivot those columns around and put them as rows if you want to. This can be useful for making your data taller. As you can see, this is making the data taller. Alternatively, I can undo this operation as well. I can do what's called an unstack. And that puts it back to where it was before. When I have data that has been stacked, or I have an index that's a multi-index, note I had columns that are multi-index, I can also have index that is a multi-index for my rows. I can unstack that and take those lower level indexes and make them into columns as well. So this is a nice little feature, just allows you to tweak your data quickly and make it flatter or taller if you need to. Some data ingestion systems or plotting systems require that the data be in a certain format, and so stacking or unstacking can help you do that. In this section, we're going to be talking about serialization, specifically serializing with CSV files. Let's do our imports. I'm going to import from the I/O built-in library what's called string I/O. This is a string buffer that allows you to emulate files. I'm going to also import Numpy as MP and import Pandas as PD. CSVs, why would we want to use them? Well, there's good things about CSVs. The good thing is that they're pretty ubiquitous. They're used all over the place. The bad thing is that CSVs don't have any type information. There's no schema information, so you can get interesting data out of CSVs. Let's look at how Pandas handles them. Let's start off with writing CSVs. Let me make a data frame here. Say my data is going to have a birth column. My birth column might be 9-1-1900 and 1-3 1904 and 2/28 1889. So I have birth dates, and I'll have names, Fred, and we'll do Marge with some accented character here just for fun, and we'll do Henry. If you're on Mac systems, you want to know how I got that accented character. I did Option E and then typed A. Let's also make a color, so these people have a color that they like. Red, blue, none. Let's also give them a number. Maybe they have a favorite number. 319. Put this in data frame now. pd.dataframe, data. And we'll inspect our data frame here. Looks like we're missing a color, so we got none here. We got our accented Marge, and we got our birth dates. Let's write this out to a file system. I'm going to write it out to this string IO buffer, so I'm going to say fout is string IO. You can write it out to the file system as well if you want to. I'll just say df2 csv, and I'll say fout. And I can inspect what the value of that is by saying fout.getValue and printing that. Here's what it wrote to the file. Note that it inserted on the left-hand side an index column and it didn't name it. This could be problematic. So if you don't want an index column in here, when you call to CSV, you can say index equals false. And in that case, it omits that. Some things that you might run into are Unicode issues. So you might have data that has bad encoding, or you're trying to encode it from the wrong type. Here we've got fout is by default UTF-8. Let's read it in here. So I'll say fout.seek 0. Now I'm at the head of this buffer, and I'm going to make a new data frame called dataframe2, and I'll say pd.readCSV. I'm going to read fout, but this time I'm going to say the encoding is Windows 1252. And let's print out df2 here. Okay, so when I do that, I see Marge now has different characters there. This is called Moji Bake or Moji Bake. Japanese for messed up words. Basically what's happening here is that I'm reading UTF-8 data as if it were Windows 1252 data. They encode characters with different encodings, and so it interprets it differently. So be careful with that. If you have a different encoding, Windows 1252 or whatnot, make sure that you specify that. And when you save it, you can save it as UTF-8 if you want. But just make sure that your encoding that you're reading or writing to is the correct one. The problem with encoding comes when you're joining multiple files or you're getting someone else's CSV file that has been combined with other CSV files and the encoding isn't consistent across those. And a lot of the time you have to deal with those on a case-by-case basis. Manually cleaning that up can be challenging, but that's what people get paid to do. Okay, let's look at CSV ingestion a little bit more. Now assume that I want to read my CSV fout.seek 0, and instead of using a default index, I want to use number as an index. I can do that as well. I can say df3 equals pd.read CSV, give it a file name or a file pointer, and say index column equals number. Let's look at the result here, df3, and we see that now my index has a name, number, and it's using those values. So that may be what you want. Alternatively, I can specify this as index column equals the position of it, 3, and I get the same result there. Now let's dig in a little bit more. df3, let's look at his D types, and we see that he read everything in as if it were an object. That can be okay, but we have dates in there, and we kind of want those dates to be dates, not strings. So let's try and see if we can fix that here. We can say parse dates equals birth. And now when we look at df3 and the D types, we see that it has indeed parsed those as if they were dates. Let's look at one more issue that we might run into, and that's missing column headers. So I've got my data here. I've got fout.getValue. Let's print that and make a new data from it. I'm going to say data2 is equal to triple quoted string. I'm going to copy this without the column headers in there. And I'll make a string buffer to hold that. fn equals string io data2. Now let's load this file. df equals pd.read CSV fn, say fn.seek 0, just so we're at the head of this buffer, and let's print df. Because I don't have any column headers, it's treating the first row as if it were the column headers. So the way to get around that is to specify a parameter called names, and we will give it a list birth, color, name, and number. And in that case, we get our column headers back. In this section, we've talked about CSVs, and CSVs are very common. Some issues that you might run into are Unicode encoding issues, or just encoding issues in general. Make sure that you have the encoding correct. You might be missing column headers, and you might have an index that you do want to use or don't want to use. We've also seen how you can encode dates with CSV. In this section, we're going to be talking about serializing JSON. JSON is commonly used for web services, and Pandas can handle JSON. Here's a data frame that we have. We can serialize it to JSON really easily. We call the toJSON method, and it gives us some JSON. We can import the JSON library if we want to here and say data equals JSON dot load s, that means string, df2 JSON. And let's look at what we get there. We get a dictionary back, a nested dictionary, which we can put in a data frame if we want to, pd.dataframe. So that's one way to ingest it. It's a lot easier to ingest JSON this way. I'm going to write my JSON string out here. JSON string equals df2 JSON. Here's my JSON string. And if I want to ingest that, rather than round-tripping it through the JSON library and passing that into the data frame constructor, I can just say pd.read JSON. JSON stir, and that gives me back a data frame. Let's assign this to a variable here, and look at my data frame, and let's look at the types of it as well, dtypes. We can see that number, because in JSON, number was actually a JSON integer, that the coercion there seemed to do the right thing. There's the number at the bottom, and you can see that at index 0, we have the integer literal 3, not the string 3. So we have objects there, so that's good. Note that our dates are strings here. That might be problematic. Let's see if we can get some dates out of that rather than strings. I'm going to try and read this again. df equals pd.read JSON, JSON stir, and we'll say convert dates equals true. Print out our dtypes here to see if this worked. We see that birth is still an object, so it didn't convert to a date. Let's see if we can convert that to a date, if Pandas knows how to do it. There's a built-in function called toDateTime. Let's pass in df.birth. Yes, we can convert it, but the convert dates parameter is not working on read JSON. Let's look at that a little bit more. pd.read JSON. Convert dates. This says the default is true, so it's already trying to convert dates, and it converts dates if the column ends with _at_time, begins with timestamp, or the column is modified or date. So since our guy doesn't fit any of those, he's not working. Alternatively, it says it can be a list of columns to pass in for dates. So let's see if we pass in a list of columns if that works. pd.read JSON, JSON stir, convert dates, and we'll say birth. And we'll say df is equal to that and print out our dtypes to see if this works. And in this case, we get that it has parsed the dates. It appears to do the right thing. We've seen how we can dump objects to JSON and we can read objects to JSON. One more thing to be aware of, when we originally dumped it as JSON, we dumped the birth as a string to JSON. If we say this new df to JSON, we see that we don't get a string output, we get a number here. So let's try and round trip this and see if we parse this, if we get a date from it. So df2 equals pd.read JSON, and we're going to read df.toJSON, and we'll pass in the convert dates parameter and say birth. Let's look at the dtypes. Run that. In this case, it says birth is an int64 rather than an NS timestamp. So the problem here is that, here's a hint, when you say df.toJSON, you can give it a date format. And if you say ISO, then it looks like this string right here. Let's put in date format as ISO and see if we get the right thing happening here. In this case, we got birth coming in as a string, and the convert date is failing on that. This is a case where you're going to have to manually cast it afterwards. pd.toDateTime on birth after the fact will indeed convert it to it. So you would have to do something like this, where we say pd.toDateTime df2 birth. So it would be nice if it handled that. It does not handle that by default, so we have to jump through some hoops to do that. So we've looked at JSON serialization, and the default types for JSON are strings, dates, and numeric types. And so Pandas can handle some of those okay, others it has to do some fiddling with. Python has another serialization format called Pickle. This is native to Python. Pandas supports that as well. Here I've got a data frame. Let's try and pickle it so I can serialize it to the Pickle format. There's a built-in method called toPickle. Interestingly enough, toPickle doesn't support a file handle, it only supports a path. So on my system, I'm going to say pickle this to foo.out. It appeared to work. Jupyter Notebook allows me to run shell commands. This won't run on Windows, but on Unix systems, I can run the cat command. And I can see that here's what it pickled it as, some binary format that Python should understand. And let's see if I can read it from that. Data frame 2 is pd.readPickle, and we need to read it from the file foo.out, and it appeared to work. So the nice thing about this is that the types are intact. So we have date time and string and int64. Because we pickled it, it knows what the types are. That's basically it. You can say toPickle, and that's a method on a data frame, and you can invoke the readPickle function in the pandas namespace. Note that again, these have to be file names. They can't be file handles, which would be nice if you wanted to pickle these over the wire. Looks like you have to put them as an intermediate step on the file system somewhere. Let's look at another serialization format, and that's using Numpy. If I've got my data frame here, I can say df as matrix, and that returns me a Numpy array. Note that the D type on this array is object. Numpy can store things pretty compact if they're the same type, and in this case we've got various types, strings, dates, numbers, and so Numpy just leaves them as objects. So it's not as compact as it could be, but if you really need it as a Numpy array, this will give it to you. And let's just round trip that. So I'm going to say pd.dataframe, and I'll take df as matrix as the input. And we see that it appears to work. One thing that we don't get is the columns. We've lost the columns here, so we need to say columns equals birth, color, name, number. And that gives us those. Let's assign this to a variable, mpdf. And let's look at our mpdf.dtypes, and everything's an object here. Everything is cast as a string. In order to change that, we can manually course them if we need to. We could say mpdf.number is equal to mpdf.number as type, and put it as an int. And we could say mpdf birth equals pd.toDateTime and pdf birth. And now mp.df.dtypes is something that's more useful for us. So that's basic serialization to NumPy. Typically where you use this is you'll be ingesting a NumPy array rather than exporting your values to an array. You can export them to an array, and one case where that might be useful is using the Scikit-Learn library. Typically the Scikit-Learn library depends on the input being numeric values, and so if you have columns that are numeric, you can say as array and feed that into Scikit-Learn. But if you've got mixed types here, Scikit-Learn round tripping is probably going to cause more problems than it's worth. In this section, we're going to be talking about serialization to Excel. Here's our data frame here. Let's inspect our D types. We've got dates and strings and integers in there. So we can call df.toExcel. This takes what's called an Excel writer, which is a file path or an existing Excel writer. So I'm just going to give it a file path here, and I'll say this is going to be in temp names.xls. Note the XLS is the non-XML version of Excel, the binary format. I'm going to run that. It appeared to work. Now it might throw an error here. It might throw an import error, and you might need to load a library. So you'd say pip install xlwt. This is the library for writing the old version XLS files. So if it throws an error, an import error, xlwt is not found, run pip install or conda install xlwt, get that library into your environment. Let's open up this file and see what it looks like. I've got LibreOffice here. There it is. Birth appears to be exported, color, name, and we even have our Unicode character. That's how we export to Excel. Let's try reading a file. I'm going to say df xls is pd.read Excel, and I will say temp names.xls. this works on my machine. If it doesn't work, you might need to say pip install XLRD. XLRD is a library for reading Excel files, just like XLWT is for writing. Let's look at the result of that. And it looks like we're pretty good. We got Unicode. Let's look at the D types here. And we got birth back as a date type. So that's cool. We're preserving the types and round tripping from the old binary format of Excel. Let's try exporting to the new format of Excel, XLSX, which is an XML-based format. So I'll say df.toExcel, and I'm going to say temp names.xlsx. That appears to run. If that doesn't run, if you get an import error, then the library that you want is you want to say pip install or concat install open pyxl. So this is a library that supports reading the XML format for Excel. This is the newer format. I'm going to open that file and let's see what it looks like here. And looks very similar, except it's using this Calibri font rather than the other font. But it looks very similar. We have dates, we have Unicode, it seems to work. And let's round trip that now. df xlsx equals pd.read Excel and temp names. Let's look at our data frame. That appeared to work. Let's look at our D types to make sure that our D types worked as well. And our D types held up as well. So round tripping to Excel works. You might need to install some libraries. These are not hard dependencies for Pandas, but if you need Excel support, then you'll have to install these libraries. In this section, we're going to be talking about how to plot with Pandas. Let's import some libraries. I'm going to import Pandas. I'll import date util, import Numpy. Let's read in a data frame. I've got one sitting on my file system here. Looks something like this. Has some Beatles albums, the year they were released, their chart position in the US and the UK, certifications, the count of the songs, and the year that the album was released. Out of the box, Pandas has plotting support, so I can say df plot, and it should try and plot. It's trying to plot, it's not putting out anything. In order to make it plot, I need to use this little snippet up here called matplotlib inline. This is a cell magic. It's a directive to the Jupyter kernel when it renders matplotlib images to render them inline. So I'm going to rerun this now and we'll see that it puts it inline here. This plot isn't super interesting per se, but maybe I want to plot the count of the songs. So I can take that series out, count songs, and call plot on that and get something that might look slightly more useful. Maybe I want to plot position. Let's plot chart position. I can say df, and let's pull out the columns that only have position in them. X for X in df.columns if position in X, and I'll plot that. That gives me something like this. Not super useful because of the limits of the y-axis. Let's see if we can tweak that a little bit. I see that when I run this, the return of the plot method is this matplotlib axes. This is different from a data frame axes. I'm going to assign a variable to that, and on that matplotlib axes, I can do things like this. I can say set ylim. That allows me to tweak the matplotlib limits of the y-axis here. And I'm going to say run from 5 to -1. Now I get something that looks like that. So it's counting down, starting from 5, going up to -1, which might make sense if you're talking about chart position. One thing that's not super useful about this is the x-axis. So the x-axis is based on the index by default, and the index is just this monotonically increasing number. If I want to make it slightly more useful, I can say I'm going to take my index and I'm going to set my index to the title column. Okay, I got an error here. It says key error title. Let's look at what my columns are. df.columns. I'm doing it in the wrong order. I need to put my set index before I filter out my columns, because at this point there aren't any columns here. So I'm going to put this here. That will return me a new data frame. And I'll plot that, and we'll see that now the index is this garbled stuff down here. At this point, I need to dive into Matplotlib a little bit more to tweak it. The nice thing about Matplotlib is you can go to the website and basically figure out how to do things. What I'm going to do here is say my labels are equal to my df.set index title.index. Those are my labels. On my axis, I want to say set x tick labels to those labels. And I'll say rotation equals 45 degrees. And I get something that looks like that. Slightly more useful. Let's tweak it a little bit more. Notice it's basically using the center of the text to line up. Let it be the center of that lines up here, the center of Abbey Road lines up here, so we get weird spacing because Sgt. Pepper's is so long that it has to push it down to line up with that tick right there. So we can tweak that a little bit more by saying that our rotation mode is called anchor, and then we get something like that. Maybe we want to change how the dots are, so we can do something like this where we say plot. In the plot, I'm going to pass some options. What's going to happen is Pandas is going to pass these down to Matplotlib under the covers. Now I have something that looks like that, maybe slightly more useful. Matplotlib gives you access to go in and pull apart all of these axes. I can take off the bottom line if I want to and the left line. I'm not going to do that in this, but just wanted to illustrate that out of the box we can plot. If we need to, we can go in and we can tweak that plot using Matplotlib constructs. Because this course isn't on Matplotlib, I'm not going to dig into that more other than refer you to the website. If you want to dig into that, the website has a gallery where you can check out various plots and they have all the code of how to do things. And that's how I end up doing things with Matplotlib. You have a basic plot and then you want to tweak it. You go in and look at their examples for tweaking it and go in and tweak it. In this section, we're going to look at how to plot histograms using pandas. Make sure we have our imports, Matplotlib inline to show our plots inline, and we'll import pandas. We're going to use our same data, our beetles data. Okay, here's our data frame. It's got various stats about Beatles albums. And if we want to make a histogram just to see the lay of the land, we can call df.hist. And pandas will automatically make a little histogram of all of the numeric columns in there. Note that the layout of this isn't quite as good as it could be. The titles of some of the subplots here in this lattice plot are overlapping some of the values of the x columns. Matplotlib actually has some code to deal with that. Let's import Matplotlib and try and use that. Import Matplotlib, pyplot as PLT. And the code to generally help you fix layout is called plt.typeLayout. So what that does is it looks through all of the plots that it finds and adjusts the layout so that they don't overlap. If I run that, I actually get an error here. None type object has no attribute is bbox. That's actually an issue. The Pandas people claim it's an issue with Matplotlib, and so hopefully it will get fixed in the future. What the issue is that down in this corner, this lower right-hand corner, there's not an even number of plots, and so the code for Matplotlib is expecting an even number of plots. I'll just show how it works if you have an even number of plots here. So I'll get the columns that are numeric columns, so I'll look at df.dtypes. That tells me my columns here, and I'll get my numeric columns, and that's going to be df.dtypes is not equal to object. That will be all the numeric columns. This is actually a mask, so I'll take this mask, 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 and I'll use this mask in my df.dtypes, and that gives me all of the columns that are only numeric. And if I call index on that, that will give me an index that has a sequence of those columns. So then I can use those columns. I can say df, use these columns here, and if we do a hist on that, it should look very similar to what we had before. Let's just take the first 4 columns so we have an even number, and we'll do plt.type layout. And you'll see that it has adjusted the layout so it looks nice. So if you have an even number of plots, that will work. Hopefully in a future version of Pandas that gets fixed. Let's look at some other options for making histograms here. Now note that on these previous calls, I called hist on the data frame directly. There's also on the data frame, there's a plot attribute, and on that I can call hist. And I'll get something like this. And here we see that year is sort of blowing everything out of proportion here. So let's tweak this a little bit. And we'll say use X for, we'll use a list comprehension to get the columns that aren't year. If year not in X. For X in, we need to put an in there. And that gives us a max of 30 there. We see that we've got this unnamed guy, which is the index. When we serialize this, this is the pandas index that gets pulled in as a new column. If we only cared about chart position, there's two columns that have chart in them. So if chart is in X, let's do those histograms there. And we get something that looks like that. Not particularly interesting. Typically, when you're using histograms, you might have a little bit more data. Let's use count songs, and let's look at what that histogram looks like. Okay, it looks slightly more like a histogram. Note that in this case, I'm not calling plot on a data frame. I'm actually calling it on the column, which is a series. Let's tweak a little bit so I call it on a data frame, and you can see that there's a slight difference here. So when I pass in a list of columns to the index operation, then I get a data frame out of that. And when I do that, you'll see that it puts the legend up there. So if you want the legend up there, you can do that slight little tweak. Let's look at some other things that we can do. We can also pass matplotlib arguments for plotting. So I can say color equals R, that means red, and alpha equals 0.3, and I get a plot like that. I can also change the bin sizes if I want to. I can say bins equals 3, and that will give me 3 bin sizes. I can say bins equals 20 and get 20 bins if I want to. I can also do things like this. I can say I want to have a cumulative plot, so set this cumulative parameter equals to true. And this is a cumulative histogram. Rather than showing the frequencies at the counts, it's summing them up. If we tweak it slightly and we say normed equals true, we add in another parameter here, then it makes what's called a cumulative distribution function. And this says that over here, frequency at 50% of the albums had more than 10 songs, slightly more than 10 songs. That's how you can read that. And you can see that 80% of the albums had 15 songs. And then we get the white album over here, which blows that out of proportion. Finally, we can also normalize our histogram. We can say normed equals true. And in this case, the sum of all of these bars should add up to 1. That's a normalized histogram. So in this section, we've looked at various ways of plotting histograms using series and data frames. Hopefully this is useful. A histogram is a nice visualization for seeing the spread of your data. In this section, we're going to be talking about doing bar plots in Pandas. I'm going to be using my same data frame here, so Beetle's data frame. So I want my columns, take all my columns for X in df.columns if year not in calls, because I don't want to use that year column because it blows things out of the water. And let's make a bar plot. In order to make a bar plot on the data frame, we can say plot bar, and that gives us this bar plot. Let's filter it by our columns here. Now it's not blown out so far. And we can see that it went through and it took unnamed 0. Unnamed 0, that's the index. We probably don't want that column as well, so we could filter that out. Or maybe we want to say pause calls, the position columns. If we care about US and UK position, where the chart ranked, we can make a plot for that. So I'm going to take all my columns, X for X in df.columns, if position in X. Let's do a plot with that now. So I'm going to take my data frame, I'm going to filter by those columns, pause call, and I'm going to call plot on the resulting data frame that gets back, and I'll call bar on that, and that gives me the positions there. Again, We have the index is this monotonically increasing numbers here, which isn't super useful. Maybe we want to see what the position was for the album. We want to use the album. So instead of calling that, we say set index on the original data frame, title. That's going to return us a new data frame. On that, we're going to use only the position columns, and then we'll plot it. We get that. That looks pretty good. Another option that we can do is we can say bar H. That gives us a horizontal bar plot. This is plotting a data frame here. We can also plot the count of the songs as a bar H. And we have a nice little bar plot for a series. So note that count songs, when we pull that off the data frame, it's returning a series. And on that series, we're calling plot and bar H there. Again, Pandas gives you the 80% plotting out of the box. You can quickly plot stuff, and if you need to dive down and tweak it further, you can using the matplotlib artifacts that it returns out of the box. But for quickly visualizing, this is great, and bar plots are a great way to tell the relative size of something next to something else. Let's look at doing some line plots in Pandas. Out of the box, when you plot a data frame, you get a line plot, and it plots the index versus all the numerical columns. In this case, I'm going to deal with the position columns, so df pos calls dot plot looks something like that. Pretty useful. We can change the axis if we want to. Other things that we can do is change the label name. Again, it uses the index by default to plot. Let's change that so it's a little bit more useful. Maybe we want to plot by year. So we can say set index, the released column, and we see that it is using those released timestamps for that down there. They don't look super useful here. Pandas tries to be smart about laying them out. Sometimes it will rotate them for you, sometimes it won't. I can specify rot equals 45 in here. That will rotate them 45 degrees. Be careful though, if your text is a different style, it might not look as good. For an example, if we use the album name instead here, then you get something like that, which is not quite as pretty as the other one. So you're going to have to go in and tweak those a little bit more. Let's look at some other examples of what we can do with a line plot. Some of the things you might want to do is change the styling on it. So you can say color equals, maybe we want one to be black, K, and the other one to be red. We can also change the line style. We can say line style equals dashed. There are various styles. We can also come in here and say marker equals plus, and it puts a little plus at each of those points. A little hard to see here with the axis as it is. Let's change that. ax.set y limit. Flip it here from 5 to -1. There you go. You have some basic plotting line plots here. This is plotting a data frame. We can do the same thing. Instead of a data frame, plot maybe the count of the songs. Here I'm going to plot a series. So I'm just going to pull off this count songs, and I'm going to plot that series. And this is complaining here because my color is expecting 2 guys to be plotting and I only have 1. Let's get rid of my limit. There's my songs over time. We can see that apparently they were very productive in 1967 and 68 and slowed down for a while at the start of 69. This is an introduction to line plots in Pandas. Out of the box, Pandas will give you basic line plots. If you want to tweak them, you can. It has some ways to tweak them, rotate the text, change the color, change the style, and also give you the underlying matplotlib handles to further tweak them if you want to. In this section, we're going to look at how to do faceting or making grids of plots. I'll use my Jupyter Magic to make sure that I inline my plots. So matplotlib inline, and I'll do my imports. Import pandas as PD, and I'll import matplotlib. Let's use our Beatles data set. So pd.read CSV. And that data set has the index column in position 0, so I'll just pull that out. Make sure our data set looks okay. Looks to be okay. Okay, let's look at fasting a little bit. We've already seen doing a histogram. If I call df.hist, it will make a little grid of plots here. And if those look okay, you can use those. One of the things that this does is it does some weird formatting on the year. You can go in and tweak the underlying matplotlib formatters if you want to. We also saw in a previous section where you could say hist and then say plt.tight layout to make sure that that layout looks slightly better. Note that tight layout won't work if you have an odd number of plots there. Let's look at box plot. We can make a box plot as well. You can ignore these warnings and the output here. And here we see that a box plot in this case looks kind of blown out because we're doing a box plot for all of our numerical columns. And the year column is when the Beatles albums came out, so those are the late 60s, and all the counts of the songs and positions are lower numbers in the ones and teens range. Let's do some filtering. Maybe we want to look at just the columns that had a position in them. I'll use a list comprehension to say x for x in df.columns if position. So if the string position is in x, that should be my position columns. Okay, there's my two position columns. And let's use that to do a box plot. Again, you can ignore those. And we can see a little box plot here. Because our samples, we only have a few samples, it's not super box plotty per se. We can verify what the summary statistics are. And we see that we only have 6 and 8 samples, and they range in the UK, they range from 1 to 3, and in the US positions, they range from 1 to 2. Our box plot somewhat indicates that, but because we don't have a lot of samples, it's not putting boxes in there. Another thing that we can do, we can use the by parameter of the box plot method to put it into a grid. So maybe you want to say box plot by year, and that pulls out the year and plots all of our numeric values by year. And that looks more grid-like and faceted. And again, if we want to tweak the axis, we can tweak the layout using plt.tight layout. We can tweak the underlying matplotlib axes as well. Another option is to do what's called a scatter matrix. In Pandas, there's a little module nested down in here called tools.plotting, and inside of that module, there's a scatter matrix function. Let's import that, and we'll call scatter matrix on our data frame, and gives us this pair plot of the numeric columns versus themselves. This might be a little bit hard to read. What it's saying here is in the first row, you see UK chart position plotted against itself, plotted against US chart position, plotted against the count of the songs, and plotted against the year. So when a number is plotted against itself, you see a little histogram type thing. When it's plotted against another column, you'll see a little scatter plot there. And note that in this case, year is using some scientific notation where it's saying 1, 2, 3, 4, 5 plus 1.965 times e to the third. So 1965 plus these values is how it's depicting year there. Again, we can play around with this. We get matplotlib objects out of it. We can say plt.tight layout if we want. In this case, I'm not sure that that helps per se. We get a slightly different output. This is an instance where pandas and matplotlib try and do the right thing, but to really get a good plot, you're going to have to manually tweak the plot and perhaps manually lay stuff out. 80% of the time, matplotlib and pandas can basically get you there, and sometimes it can't get you there, and sometimes that's due to your data. We maybe don't have a lot of data here, and so that makes the plotting hard, or maybe we have too many columns or whatnot, and so we have to go in and manually tweak stuff. But I just wanted to give you an overview of some of the various ways to plot in pandas, and we saw that we can, for example, if we say hist, that will give us a grid of plots of histograms of our numeric columns. If we do box plot and do the by parameter, we can also do faceting by another numeric column. And using the scatter matrix function from pandas, we can also make a little faceted grid of values. In this section, we're going to be talking about dealing with time and time series in pandas. Let's import a few libraries. Import pandas as PD from pandas.io data. Import data reader. We'll import Numpy. And we'll import dateutil parser. I'm going to import my Beatles dataset again. Read CSV. Let's look at my dataset here. dtypes. Released is an object. One would hope that it would be a date instead. So let's see if we can make it so when we read it, it comes in as a date. Let's try and read it again. This time we're going to say parse dates equals released. And we'll say df.dtypes to see if that worked. It's still a string, which isn't useful. Let's try another option here. Let's try again. df equals pd.read CSV, and I'm going to read the Beatles. I'm going to say converters equals a dictionary that's going to map the column name, so released. And what I want to convert, I want to use the parse library that I imported above from the dateutil.parse. Let's see if this works. Parse works in this case. This is an interesting thing that I've dealt with in Pandas. If we look at pd.read CSV, there's a bunch of options in here. Parse dates says you can pass in a list of names to parse, and the date parser is a function to convert a string of columns to an array, and the default is none. It says default none up here, and then says default uses dateutil's parser.parser to do that. Let's try one more time with this guy up here. If we can say date parse, the parser does not work. Seems to be a wart with pandas that I need to explicitly state which parser I want to use for a column to convert it to a date. It'd be nice if when I said parse dates equals released, if it actually threw an error, if it couldn't course that into dates. That's one of the things I've noticed when dealing with dates in pandas. Let's look at some more dates and converting other dates here. I'm going to make an array of dates. Dates equals, say 10/10/2015. I'll say 9/8/2012. Say 2/2014. September 17th, 2000. And I'll say foo. Pandas has a PD2 datetime built in. Let's pass that in there and see what happens. Okay, so it got an error here. It complained, and that's because if you look at the documentation for this, there's an errors parameter, and the default is to raise an error. The other options there are to ignore or to coerce. Let's look at those quickly. Errors equals ignore. And when I ignore, note that I get back a D type of object back, which may or may not be what you want, but I would assume that it's not. The other option is to say coerce, and when I coerce, I get back a date time object out of it, but this foo string is coerced into a not a time object. Be careful when you're coercing. If you get an error, it means you might have to deal with missing values or whatnot, and you can get not a time by setting your errors parameter equal to coerce. Note that this does not return a series, it returns a datetime index. So in order to get a series out of this, I need to pass it into a series. Then I will have a series here that has a datetime of that. Once I have this series, I can do various things with it. I can look at a DT attribute, datetime properties, and on that I can say year, that will give me year. I can say month, that will give me the month. I can say hour, that will give me the hour. So I can do various things with that, which is handy for pulling out parts of the date and putting them into their own column if I need to. This has been a brief overview of dealing with time in Pandas. The main takeaways are when you load a CSV file, you need to make sure that your columns actually are coerced into dates. Check your dtypes attributes to make sure. Once you've coerced, you have the DT property that you can access to pull off various parts of the time. In this section, we're going to be talking about window functions. Window functions are used in SQL OLAP type operations to do group bys over date ranges and process date ranges. Pandas has various ways of processing dates and series of dates, and so let's look at some of them. I'm going to make an index here, and I'm going to say PD date range. So this is a built-in function in Pandas. And I'm going to say I want to start at January 1st, 2000 and have periods equals 500 and the freak is going to be days. We can look at that and we have this date time index that's 500 long and is about 500 days, about a year and a half or so. I've imported the Numpy library here. Inside of that there's a random function. So I'm going to make a series here using that. The series will be pd.series. I'll make it by calling np random, and I'm going to make it the length of my idx. That's how many random numbers I want. And for my index, I'm going to use idx for that. Let's look at my series now. And the resulting series has an index that's time-based, and it has some values in there. So I can do normal series operations to that. I can also do other things that might be useful. So I can make another series, and I can say this series is the series plus the series shifted by 2 steps. Let's look at what that looks like. You see that the first 2 index elements are not numbers. That's because when you shift a series by 2, it's shifting it down 2, and there wasn't anything to shift down. It just fills in the blanks with not numbers. And so when you add something to a not number, you get not number as a result. But if you have 2 time series that you want to add or you want to shift by a day or a week and do operations on that, Pandas will allow you to do that. Another useful option to do on a series is I can say resample, and I can resample by various things. I can resample by year, and I can resample by month if I want to. And it's going to take the mean in there and give you the mean over all of those periods. So it quickly allows you to resample. So this quickly allows you to apply some aggregate function over a period. Let's look at the help for that. There's this rule string. The default sampling is mean. You can see some examples here. So this shows you how to do 3-minute bins. There's a little language you can use, 3T, 30S, 30-second bins. So if you want to know what the rules are, you can go to the Pandas documentation, this guy right here, and he gives you the aliases for doing these resamplings. So for example, I can say Q, and that will be the quarter in frequency. Let's show an example of that. There's my quarter in frequency. Let's look at another example here of processing data. I'm going to load the S&P 500 data. I imported the data reader, and I'm going to say I want to load the S&P 500 data, and my data source is going to be Yahoo. There we go. Let's look at what we got here. I'll transpose it. We have open and close starting from 2010, January 4th, and I believe it goes up to the current day. Let's look. Up to the current day, it gives you the results. One of the theories about when to buy or sell stock is called the golden cross. If you have the 50-day mean and the 200-day mean cross, that's an indicator that you might buy or sell. If the 200-day mean crosses the 50-day mean, that means that the average stock price over the long term has been going up, but recently it's been going down, so you might want to sell. So let's look at how we could do that here. I can say SPY mean 50, and I can say pandas rolling mean, and I'm going to pass in the close value here, and I'm just going to take 50. And I'll say SPY mean 200 equals PD.rolling mean SPY close 200. Let's look at what that does here. We get knotted numbers here because we're at the start and there aren't 50 values before it, so it can't do the average here. But if we look at the tail, we see that there are values there. The rolling mean, there are various rolling methods that you can do in Pandas. You can do rolling apply and call your own function to do whatever you want. And there are various other ones: rolling correlation, rolling count, rolling covariance, rolling kurtosis, rolling max, rolling mean, rolling median, and rolling min. These are all useful methods to do analysis over time series. Let's look at plotting. I've got this SPY guy, and he has index as a date. Let's plot him, see what happens when we plot spy.plot. By default, it's going to take the index and it's going to plot all the numeric columns. Lots of data in there, and some of them blow out the other ones. So what I'm interested in is the close and the mean columns, so we can look at this golden cross metric. Let's see if we can plot that. So I'll say SPY, and I'm going to plot the close column and the mean 50 and the mean 200. And there we go. We can see from 2010 to now how the S&P 500 is done at the close. And the green line is the 50-day mean, and the red line is the 200-day mean. And so the theory behind this golden cross is that when the red line goes above the green line, the 200-day moving average is above the 50-day moving average, that is an indicator that the stock is falling and that you should sell at that point. And conversely, when it dips below, at the point it dips below, it's an indication that the stock is now on the rise and that you should buy at that point. Note, I'm not a financial advisor or anything, that's just a theory. But we can see one line of code here, and we can easily look at this and do some analysis on this. So again, out of the box, Python has great support for time series. It has plotting and allows you to do cool things like this. In this section, we're going to look at how to do machine learning with the Scikit-Learn library, and we're going to have data in Pandas, and we're going to do some classification with that. So here I've got some imports. I'm importing Pandas, and I'll import the Scikit-Learn library. More specifically, I'm going to import the ensemble module, which allows me to create what's called a random forest. Let's run my imports here. We're going to be using the iris dataset. You can go to the UCI machine learning repository, and you can find this dataset. It's a pretty common data set among data scientists. It came out in a paper in the 1930s, and the data looks like this. It's got 150 samples of 3 types of irises: setosa, versicolor, and virginica. And it's got sepal sizes and petal sizes in there. So it's typically used to show how to do a classification, how to use the sepal and petal sizes to map to one of these classes of iris. So let's take this data URL and let's load it into Pandas. I'm going to make a data frame, so I'll say pd.read CSV. I can pass in a URL here. Now the data set didn't have any columns, so I need to write the columns here. Sepal length, sepal width, petal length, and petal width. We also have a class column at the end. It looked like that ran. Let's inspect our data. I'm just going to transpose it. And we see that we've got 150 samples here of 50 of these 3 different kinds of irises, and they have the sepal and petal sizes. We should be good to go now. Let's do a little bit more inspection. We can say df and say class and look at the value counts, because that appears to be a categorical data set. And we see we have 50 of each of those. Let's just inspect the types and make sure that our types are good. So we have floats and we have strings for the class. That should be okay when we're doing a classification to have numbers as the input. That's good. How we typically do machine learning is we create some variables. Among people who do machine learning, they typically call these variables X and Y. More specifically, the input is called features, and they call that capital X, and the output or the target is called Y. So I'm going to take my columns here, and I'm going to make capital X That's going to be taking my data frame and using a slice of my columns. I'm going to use all my columns except for the last one, except for that class column for X. That's going to be my features that I'm going to say, given this input, this shape, I want to train my classifier to predict Y, which is going to be the last column here, or the class. Okay, now I have X and Y. Now I just need to make a classifier, and I'm going to make a classifier called a random forest classifier. So that's in the ensemble module. I just create an instance of that. And to train it, I call the fit method. The nice thing about Scikit-Learn is that it has various classifiers in there, so you can try using different classifier models, and they all implement the same interface. So I just call fit with X and Y. What that does is under the covers, it tells the classifier, when you're given this row of input, X input, the result of that should be Y. So train yourself so that when you get input that looks like this, you'll predict something that looks like Y. Let's run that. And it looks like it fit them pretty good. Now that we have our classifier fit, what we can do is we can make predictions from it. I'm just going to examine our data frame a little bit more. Let's look at some summary statistics by class. I will group by class and call describe, and let's use all the columns except for the last one. Okay, so we can see that for Setosa, the average sepal length is 5 centimeters, the width is 3.4, petal length is 1.5, and the petal width is 0.2. And we can see we have summary statistics for each of our 3 families. Now let's do a prediction. Scikit-Learn, they all follow the same interface, so if I have another algorithm classifier that I've trained, I can use the same interface to do a prediction. To do a prediction, I just call the predict method. And I'm going to pass into predict a vector of input. So let's look, and maybe we'll say, given iris setosa here, let's take this as input and see if it predicts iris setosa. So I got to tweak this a little bit. It's got tabs between there when I copied it. Lo and behold, it did predict iris setosa. So perhaps our model is doing okay. Let's do another prediction here. Let's take the 75th percentile of Virginica here and see if that works. Again, we call the predict method, and we pass in our data set of what we want to use as features, and that appears to work as well. So in this module, we've looked at how to load data from a machine learning data set into a data frame, how to pass data into a classifier, and how to make predictions. In this section, we're going to be looking at feature vectors. That's the input that goes into a classifier or a regression model. I'm going to do a different thing now. I'm going to do what's called a regression. We looked at a classifier. A classifier takes features and predicts a label. A regression takes features and predicts a value. So it's a continuous value rather than a label from a category. So I'm going to use what's called a random forest regressor, which is similar to a classifier but does regression instead. Let's look at my columns. So these are the columns in my data set. I'm going to try and predict sepal length now from everything else. So from sepal width, petal width, and class. So I'm going to make a new X here, and I'm going to say X is equal to df. And I'm going to take my columns, and I'm going to start at index 1 and go to the end, and Y is going to be df calls 0. That works. Let's stick this into my regressor. So I say regress.fit X and Y. And when I run that, I get a value error, and it says cannot convert string to float. So the features that feed into my model need to be numerically encoded. Pandas can help me with that. Pandas can create what are called dummy variables. There's a built-in function in Pandas called getDummies, and it will allow me to encode this class variable. And basically what we can do is take the single series class and pull it out into a data frame with 3 columns that have Boolean values 1 or 0, depending on whether the class was there or not. So iris setosa, for everything that had iris setosa as a value, it will get 1, and 0 for everything else. Likewise for the other columns. Given that, we can make a new x that should work for our regressor. We can say x is equal to pd.concat. We're going to join our data frame, and we're going to take the original data frame, and we're going to use the columns from 1 up to, but not including the class. And we're going to concatenate that with get dummies from df class. And we're going to do that along axis equals 1. Let's run that and look at x now. Okay, now here's our feature vector. Instead of having strings, we've got iris setosa, iris versicolor, and iris virginica as input columns. That should be okay. Let's try and fit our model now. I'm going to say reg.fit x and y. It gives us back a random forest regressor with these hyperparameters that are tuned to our input. Let's see if we can do some predictions now. I will say reg.predict, and I'm going to predict that if I got 2, 1.1, and I had a versicolor here and 0 for the other two, what will be the sepal length? 4.48. That could be a good value here. Let's describe our original guy. Group by class, and I'll say describe, and I'll take my columns from up to, but not including the last guy. And I said 2 and 1 and 0.1 and 4.48. So that's around the minimum there for iris setosa. That seemed to work okay. Let's do one more prediction here at the bottom from Virginica. Reg.predict, and I'm going to predict Virginica. Let's do this 75% here. See if it gets around 6.9, 3.2, 5.8, 2.3, 0. It's not setosa, it's not versicolor, but it's Virginica. And I get 6.75. So pretty close to 6.9. The model seems to be performing okay. This shows us how we can use pandas to quickly create these dummy vectors and feature vectors and use them in machine learning. The nice thing about Scikit-Learn is that the input that it takes in is expecting to be a Numpy array, and Pandas basically conforms to that same interface. So if we have numerical values in our data frame, Scikit-Learn will accept that as input as well. And it allows us to munch the data and get the data into a form where we can use it. In this section, we're going to be looking at an infographic I did for the Utah Avalanche Center. This infographic was created by crawling the data on the Utah Avalanche Center website, processing it using Python, creating some charts, saving them as SVGs, and editing them in a tool called Inkscape to create this infographic. So you can see this talks about the deaths from 1995 to the present. And we have some summary statistics up here. We have a little plot of deaths over time. We have the locations of these avalanches where they occurred on a map. We have the types of triggers that triggered the avalanches. We have a little histogram that's sideways here that says what the elevation is where the avalanches typically occur. We have another chart here showing the slopes of the avalanches, and a little graph here showing the aspect. The aspect is the direction of the slide, so north facing or east facing or whatever. Let's look at how I did that. Let's go to the Utah Avalanche Center website, and if you go there, you'll find a detailed info section, and in there's a fatalities page. And on that page, there's a table that has general data. If you drill and you get to a page that looks like this, that doesn't have table, but just has information in it. So my plan of attack is to crawl the general data here, and then for each general avalanche information row that I have, I'm going to drill into that details URL, and I'm going to crawl the data in there. I'm going to throw all of that into a list of dictionaries. It will be key values. The column name will be the key, and the value will be the cell value. And then after that, we can put it into Pandas and start cleaning it up. In order to crawl this, I'm going to use a tool called Beautiful Soup. And I'm going to use another tool called Requests. These are both third-party libraries. You can pip install them. The nice thing about this Beautiful Soup guy is that it treats HTML that isn't particularly well-formed as if it were well-formed, and gives you a nice little tree that you can crawl down or you can query. Requests is a library that just allows you to quickly make HTTP requests in an easy manner. We'll see an example of both of these in this code here. So I'm going to import both those libraries, and I'm going to import Pandas. And let's start writing my crawling code here. My base URL is https utahavalanchecenter.org. And I'm going to make a URL that has the fatality information. That's going to be base plus avalanches fatalities. I'm going to make a variable called headers. This is going to be my HTTP request headers. And let's make a function here called get field name value. And it's going to take element. This is a beautiful soup element, and it's going to pull out the key value pairs for that. Let's look at how we'll do that. Look at the page source for this. So I'm going to search for avalanche fatalities, and we'll see the table right below that. There's the title has it, and here's another one. So the interesting thing in here is that there's an ID in a div tag called content, and this is the content of what's interesting on the page. So we can search for that and start our search by looking inside of that div. Now below that, we see there's a table, and in the table, it's got a header row, and it also has normal rows. The interesting thing about these rows is that each of these rows has a TD element, that's the cell, and the TD element has a class in it, and the class starts with views-field, and it says like region forecaster or region forecaster-1 or trigger or killed. Those are the key names at the end of those class values, and the values are just the contents of the cell. So that's basically the logic that we're going to go through to pull off those key values in there. Write some code to do that now. Get field name value is going to take a element. This is a beautiful soup element. It's going to get all the class attributes. So we're going to ask lm.get class. We're going to put that in a variable called tags. And we're going to make another variable called start. It's going to hold views-field-field. That's the start for our key name. And we're going to check and see if any of our tags start with that. For t in tags, if t.starts with start, we're going to say return t. We're going to slice t. We're going to slice it from the length of start to the end. And we're also going to return the value here. So we're going to take an empty string and we're going to join it with elem.stripped strings. So stripped strings here is a property that goes through all the sub-elements and pulls out any text values and returns those. So that will be the value there. I've also got one more type of key value, and that's a URL. So if t, the tag is equal to views-field view node, that means it's a URL. And so I'm going to return as the key URL, and the value is off the element. I'm going to look at the A attribute and pull off the href attribute from that. Otherwise, I'm going to return none. That should parse an element and give me back these key value pairs. Let's go over the rows and find those elements. So I'm going to make a function called get avalanches. It's going to take a URL to start with. I'm going to make a request using the request library. So I'm going to say r.get and get the URL. I'm going to pass in my headers. I'm going to pull the data off of that result. So request has a text attribute, and that's the text of the page. With that data, I'm going to throw it into beautiful soup, beautifulsoup.data. I can also say what kind of markup I want to use. By default, in the current version of Beautiful Soup, it does HTML markup, and the documentation isn't going to say here, but it's going to throw a warning when I parse this. We'll see it. It'll be okay. Future versions of Beautiful Soup, I need to be more explicit about what kind of data I'm throwing in there. So my content, I'm going to be looking for that content ID. So I say soup.find and the ID content. I'm going to find all my rows. I say content.find all tr. And then for every row, I'm going to accumulate results. For tr in trs, tds equals tr.find all. So find all the cells in my row, and I'm going to accumulate the results of those into a dictionary, mapping the keys to the values. For td in tds, for every cell in my row, I want to get the name and the value. And we can get those by calling our little function get field name value. We're going to pass in td. And if we got a name back, we're going to say data name equals value. Otherwise, we'll just continue. Skip that cell. Some cells don't have data. And if we have data at the end here, we'll say res.append data, and we'll return res. I ran that. I've got a syntax error, line 12. LFT assignment, that should be equals. Let's try it again. Looks like it worked. Let's try and crawl the main page for just what avalanches occurred. Get avalanches URL. I got an error here. Let's see what error I got. The error says connection aborted. I actually expected this. I knew this was going to happen. So what's happening here is that after I crawled this web page last year, the administrators made it so it didn't like crawling with Python. So I'm going to emulate a Mozilla browser instead of the Python. I'm going to change the user agent HTTP parameter that gets passed in with requests. And I'm going to just change it to Mozilla /5.0. Let's try again. So I'm going to make a variable called AVS and get avalanches with my URL. I get my little warning here that Beautiful Soup wants me to say HTML parser in there. And I get another error here, if t in tags. So this should be for t in tags, and we'll change the Beautiful Soup error as well, so we don't get that warning here. We're passing in HTML into Beautiful Soup, so use the HTML parser. Let's run it again. We appear to be slightly more successful. Let's see if we can throw this into a data frame. We appear to be doing pretty good here. We've got basic information and we've got this sub URL that we can crawl. In this section, we looked at how to crawl using the Beautiful Soup and the request libraries. In the next section, we'll cover that a little bit more. In the previous section on crawling with pandas, we looked at crawling a table. In this section, we're going to look at crawling just HTML without a table. We'll be diving a little bit more into using the request library and using Beautiful Soup to create a data frame. Okay, now we want to crawl the details page. Let's look at the details page. So inside of here, we've got a details link, which is that URL, and we can see that we don't have a table here, but we've got something slightly different. Let's look at how this is formed. I'm going to search for observer space name. Here's observer space name. Again, we see that there is an ID of content here. We're going to search for that ID of content. Inside of that is what we're looking for. And we're just going to go through and find every guy that has a field class. So you can see that there's a field class here. Pretty conveniently, there's a field label class inside of that field class. So we're just going to look for all the divs that have a class of field. And then inside of those, we're going to look for field label to get the key. We're also going to look for field item to get the value. So that's the basic gist of what we're doing. Let's write some code to do that. I'm going to make a function called get avalanche detail. And it's going to take a URL and it's going to take a dictionary. We just created this nested list of dictionaries. It's going to take one of those dictionaries and it's going to update that dictionary. We're going to make another request using the request library. We're going to use the URL and we're going to tack onto the end of it the detail URL that we get from the dictionary. We can see that in the data frame above there. We're just going to tack that bit on and we're going to use our headers to emulate a browser. Off of that request result, we're going to get the text attribute and stuff it into a variable called data. Now with all of that, we'll throw that into Beautiful Soup and we'll say we're going to use an HTML parser. We're going to find our content. Again, that's the ID is equal to content. Soup.find ID equals content. Now we're going to find all of our field divs. To do that, we're going to make a variable called field divs. We're going to say content.find all. I have to say class underscore equals field. In this case, I have to say class underscore because class is a reserved word in Python, and Python won't let me use it as a parameter name. Now we have these divs. I'm going to say for div in field divs, loop over them. I'm going to look for the labels. If I find a label, I'm going to look for a field item as well. Let's find the key element is div.find class underscore equals field dash label. If we got one, if key element is none, if we didn't get one, we'll continue, try and keep finding one. Otherwise, our key is going to be the empty string, and we're going to join that with the key element stripped strings. And let's try and get the value now. I'm going to put this in a try statement because sometimes I have attribute errors here. So the value element, similar to the key element, is going to be div.find class underscore equals field dash item. And the value is going to be the empty string join value element stripped strings And I need to do a little bit more here. I'm going to replace the hex character A0 with a space. Notice that some of the results that I get back from crawling aren't super amenable, so I'm just doing some cleanup there to fix them. Attribute error. If I get an attribute error, I'll pass. If I've already got my key in my dictionary, if key in item, then I'll just skip that key. Otherwise, item key equals value. We'll just return our item. So now we should have updated our item with the details. Let's make another function, get avalanche details, that will go over all the avalanches and get all of their individual details. So it loops over them. Call it get avalanche details. It's going to take base URL and it's going to take this list of avalanche dictionaries that we previously crawled. We're going to accumulate the results in a list for item in AVS. Item equals, we're going to get an updated item from get avalanche detail, and we're going to pass in a URL and the item. And we'll append that to our result and return our result. Looks like that should work. Let's try it out and see. I'm going to use the cell magic time to see how long it takes. Typically this takes around 2 minutes or so to crawl the whole website. So get avalanche details, and we're going to pass in our base URL and the avalanches that we crawled. Looks like we might have success. Let's throw it into a data frame. We've got a list of dictionaries. We can simply throw this into a data frame. Cool. So I'm going to save this to CSV, and I'll put it in temp ava-raw.csv. Okay, so in this section, we looked at using the beautiful soup and the request libraries to pull data off of a web page. These are nice little libraries that allow us to pretty easily pull data off, and we put it into a list of nested dictionaries, and with that we can throw it into a data frame pretty easily. In the next sections we'll be looking at munging this data and tweaking it so that we can make our infographic. In this section we're going to be talking about munging data. As Big Data Borat says, in data science, 80% of time spent prepare data, 20% of time spent complain about need for prepared data. Basically, Pandas lets you sit in it 80% of the time and munge data and prepare data. When you're doing a data science project, most of the time you're tweaking with the data. Let's look at tweaking this avalanche data. We crawled it last time. I'm going to load this data, pd.read CSV. I've got a copy of it here. So the first thing I'd like to do when I load it is just inspect the data types. And we'll see that there's some numeric data types and some float data types. Another quick thing to do is to do a describe on it so we can see what we've got in there. Unnamed 0, that's the index from our previous save that we probably will just ignore. Buried fully, buried partly, those look like numeric values. The minimum for buried fully is 1, which makes sense. You could imagine that if an avalanche where someone is killed, someone will probably be buried fully. But it's possible that it could be 0, that it could be buried partly and still killed. Minimum number carried is 1, minimum number caught is 1, minimum injured is 1, minimum killed is 1. The minimum slope angle is 10. There's video, it's all not in numbers, and number killed is 1. This looks pretty good. The first thing to sort of notice when we look at this data frame is that the columns have a colon at the end of them, or a good deal of them do. So let's clean that up a little bit. Let's get rid of those columns. So I'm going to do that. I'm going to use the rename method, and rename allows you to pass in a parameter called columns that says, I want you to rename some column based on a dictionary. I'm going to do a dictionary comprehension. I'm going to loop over for x in df.columns. I'm going to take my column names, and I want to replace x with x, replacing a colon with empty string. Let's run that and see what that does. And we see that we no longer have colons at the end of our data frame. Let's look at some other columns. Another one we might want to look at is aspect. Again, this is the direction of the hill. Aspect value counts. If I have categorical data, I like to do value counts here. And I see that typically fatal slides are to the northeast. This makes sense because that's where the good snow tends to be if you're a skier. It's typically shaded in the northern hemisphere, and so it doesn't get melty, and it's more powdery and nicer to ski on than south or west facing aspects. Let's look at some of our other categorical data. DF, avalanche, problem. And again, to just inspect these, I like to do value counts. And we see persistent slab is the #1 type of avalanche problem. Other information that might be interesting, avalanche type, and this is categorical, so again, value counts here. And hard slab is #1, soft slab is close behind it. What else can we look at? depth, let's inspect the depth. The depth here, look at the type of this, it's an object, so it's actually a string. It has numbers that look like they could be feet or inches. So this is problematic because most computers don't understand how to deal with such numbers. So let's write an example of munging this. I'm going to import the regular expression module to do that. And I'll write a function called 2 inches, where I'm going to convert these things to inches. So I'm going to take some original value and I'm going to convert it to numerical inches. Make a regular expression. I'm going to make a raw string. In order to make a raw string in Python, I put an R before the string. It'll be a triple quoted string because I'm going to have double quotes and single quotes inside of it for feet and inches. So I wanted to match. I'm going to make a thing that matches any digit followed by a period, and that can be optional. Also, that can be followed by another digit any number of times, and that can be followed by a single quote. So that would be 3.5 feet, what we see up there on row 83. And so that whole thing can be optional. So that's to match the feet. Let's make another regular expression that's going to be basically the same, but we're going to replace this single quote with a double quote to match inches. There's our regular expression that will match feet or inches. Now the text will be the str of the original that's sent in. We need that because not a number comes in as not text values, so we need to convert it to text values. So if the text is equal to not a number, when we convert those not numbers, they'll be lowercase. We're going to just return the original. We'll return the original, not a number, or float value. I'm going to make a match object, and I'm going to call the re.search function, and I'm going to pass in my regular expression and the text. So I'm going to match that text against the regular expression. I should get a match object out of there. I'm going to say I want my feet to be the second group. How I get group is I come up here and count the parentheses. So this parenthesis here will be the first group. In this case, it's counting starting at 1. It's 1 base counting. So the second group will be this guy here, which should be a digit preceding this single quote. So this should be the feet. I don't want to match the first group, which would be that, because that will include that quote there, and I don't want that quote. If I don't have that group, the regular expression will return none, and if I don't have it, I'm going to say 0. So this is a conditional expression, feet equals mo.group2 or 0, and I'll do a similar thing for inches. Inches equals mo.group, and for this case, I'm going to want group 5. Again, to count those groups, I'm going to start at the first left parenthesis and count that as 1. So there's 1, 2, 3, here's 4, and I want to do 5, this guy right here. That will give me the inches without the parenthesis. If there aren't any inches, I'll return 0, and I'm just going to return float feet times 12 plus float inches. There's my little regular expression to convert these things. Let's test it out. 2 inches, and I'll pass in 18 inches, and I'll do another one, 2 inches, and I'll pass in 2.5 feet. The first one gave me back the float 18, and the second one gave me back 2.5 feet is 30 inches. That looks good. Let's apply it to our data frame here. Make a new column called depth inches, and I'll say it's taking the depth column and applying the 2 inches to it. At this point, I can say df depth inches, and I can inspect it here. I can also say df.depth inches.describe, and I can get summary statistics for that. So that's how we can do some basic munging. We'll look at some more munging coming up. Let's look at more munging of the data. We've got to clean it up a little bit more. We've got our data frame here. Let's look at the occurrence date of when the avalanche occurred. So we have this column here, occurrence date, and the type is object. It's a string. Let's see if we can make that into a date. I'm going to try using my handy toDateTime function from Pandas. Let's throw that into there and see what it does. Lo and behold, it looks like it does the right thing. We get a date time out of that. So that's good. I'm going to copy this guy and I'll say df year equals this. I'm going to pull off the dt attribute and get the year out of that. We can also get the date of the week if we want. That may or may not be useful by just pulling it off of the occurrence date. Let's put in a column for date of the week. So date of week equals df occurrence date. And I'm going to apply a function to it. I'm going to apply a lambda function. We'll take the string in, and if you recall, the string looks like that. If we split it on a comma, the first element will be the day of the week. So we'll say x.split and return the first one. Let's look at date of the week now. So this should be categorical, so I can use value counts on it. There we go. Apparently, you shouldn't ski on Saturday if you want to avoid avalanches. Bad joke, that's probably not the case. Probably just happens that more people are skiing on Saturdays, and so they get caught in avalanches more often. Let's look at some more munging that we can do here. Another column that we have is vertical. This is how far the avalanche slide was, how many feet the slide ran. Top one here is 1,500 feet. The next one is 200 feet. We've got one that's almost 2,500 feet. And we've got other values in there. So this should be a numerical column, but we've got values such as unknown and NaN. So it's not numerical. Let's fix it so it is numerical. Make a new column called vert. And I'm going to say take df.vertical. It's a string, so we're going to access the str attribute and call replace, and we're going to replace unknown with NaN, and then we're going to tweak that a little bit more. We're going to take the vert and fill NA. Actually, when we replace it with NA, I'm going to cast it as a type, and I'm going to say as type float. So now I should have numerical values, and I'll fill the NA values with df vert median. Whether that's correct or not, I'm showing an example of what you could do. In this case, unless you know where it is, median may or may not be a good solution. Maybe just to leave it blank would be another option. That's for you to decide on your data analysis project, how you fill in or how you handle those NAs. Another option is to just drop them. In this case, people were killed in these slides. I don't want to drop those just because I don't have details about how big the slide was. So now df.vert should be a numeric value, and if we say describe, that tells us that the average slide was 650 feet, the median was 600, the max was 2,500, and the minimum was a 50-foot slide. Very good. Let's look at some more cleaning up that we can do. Another thing that might be interesting is the coordinates here. So this is the latitude and longitude. Note that this is a single column and it appears to be a string. Some values are missing. Others have latitude and longitude as a single string. Let's pull those out. Let's make a latitude column and a longitude column. Here's how we could do longitude. Longitude is going to be the second element of that guy. So I'll make a function called def lon, and it's going to take a value, and the value is going to be this coordinate column, a single cell from the coordinate column. If calling stir on val equals nan, then I'm just going to return a float of nan. Otherwise, if I got a value, it's going to be a string. I'm going to take that string, which is val, I'm going to split it on comma. I'm going to take the last guy, -1, and I'm going to course the whole thing into a float. I'll add a column called lon, and I'll say df.coordinates apply ln. Let's inspect it now. If it worked, this should be numerical, and describe should work. It appeared to work. The minimum was 112, the maximum was 0. Apparently there's a number in there where maximum is 0, right here, 21. Let's look at that really quickly. df iloc 21. It was December 31st, 2007, and for some reason they don't have coordinates in there. Let's make latitude as well. I'm going to do latitude exactly the same as I do longitude, but I'm going to inline it into a lambda function so you can see lambda functions if you're not familiar with those. So df lat is going to be df.coordinates apply. I'm going to apply a lambda function. It's going to take x, and it's going to say if stir x not equals nan, then I want to return x.split. This is called a conditional expression. I can use a conditional expression in a lambda. I can't use an if statement in a lambda. I'm going to split on comma, take the first element, which is 0, cast it into a float. Otherwise, I want to return float nan. And that appears to work as well. Let's just validate it. df.lat describe. And we got values there. Again, we had a min 0, so we've got this problematic number that we'll probably have to deal with somehow. Okay, that concludes our munging with data. We've taken a few columns and tweaked some of them, added some new ones, applied functions to clean them up a little bit, done some string operations. And this is what I appear to spend a good majority of the time doing when I'm messing with data, is actually understanding columns and dealing with people's messy data. In this section, we're going to look at plotting some of our data. We can do such things as simple histogram plots. So if we look at df.dtypes, anything that's numeric in here, we might want to do a little histogram to view it. df.lon hist, we just made the longitude, and let's look at a histogram of it. Okay, it's not appearing here. We need to do matplotlib inline directive. I'll stick that in here. Matplotlib inline and try it again, and we see we've got a lot of them around -100, and this outlier at 0 is throwing it off. So maybe we want to do something like this. Filter df.lon is less than 0 and do a hist on that. We see a little bit more fidelity when we take out that outlier. Let's look at depth inches. df.depth inches hist. And we see that a good majority of these avalanches have a depth around 40 or so. So there's a basic histogram, allows us to see the lay of the land for numeric data. Other stuff that we can do, we have longitude and latitude, so we can do a little scatter plot on that. I can say df.plot scatter lat lon, and I get something like this. Again, we've got our outlier there at 0. Let's do some filtering. df.lat greater than 0. That looks a little bit better. So we've got a little concentration of plots of avalanche in there. That could be due to activity or high use, or it could just be really weak snow. What'd be nice is to actually throw this into a map and have a map that we can look at. I've messed around with doing this with matplotlib and seemed to be kind of painful and not as much fun as I would have liked. I ended up doing 2 different routes. One is using Google Maps. There's a library called Gmaps. You might need to pip install Gmaps. And if you've got it, you can do something like this, where I can say gmaps.heatmap x for x in zip. I need to make df.lat and zip df.lon. Okay, let's look at the result of that. These should be happening in Utah, and I'm not seeing anything there. So let's try again. Let's do a little bit more filtering. So I'm taking x for x in zipping the latitude and longitude, and I'll say if stir x0 is not equal to nan. There we go. So this is a case where having nans in there is throwing off the third-party library. And we can see these little green spots here, which correlate to where the avalanches happen. One more little tweak that makes this slightly easier to read. There's a parameter I can pass in here called max intensity. And if I say 1 here, it makes things slightly easier to see. Let's zoom in. Rather than staying green, they turn red. Because the mountains are also green, the red stands out a little bit more. And so if you're familiar at all with ski resorts in Utah, Google Maps actually shows them here. Alta is a ski resort, Brighton is a ski resort, Solitude. Another one down here is Snowbird. We've got Park City over here. You're seeing a lot of avalanches happening in or around ski resorts. What happens a lot of times is skiers take these lifts to the upper peaks and then go off the backside because there's fresh snow and get into problems. This is nice because it's Google Maps. I can zoom in and out and pan around and explore my data. I'll show you one more option for plotting maps. It's another library and it's called Folium. It's not based on Google Maps, but it's based on OpenStreetMap. And you might need to pip install Folium. In this case, if I'm using Folium, I need to do a little bit more. I'm going to import some of the IPython libraries that allow me to embed HTML. So what I'm going to do here is write a little function that allows me to make a map, inline map into my HTML. I will have a map that I pass in. On my map, I'm going to call the build map method, and I'm going to return HTML, and it's going to be an iframe, and it's going to have this source doc attribute and style set as well. Style is going to be width 100%. Height is going to be 500 pixels. We'll also close my iframe. I'll call format on that to stick in the source doc here, and the source doc is going to be map. I'm going to access the HTML attribute of that and call replace. I'm going to replace a single quote with escaped quote. If you ask me why I'm doing this, because I messed around with it and this is what I needed to make it work. And I need one more function here. Here's my inline map. I'm going to make a function called summary. It's going to take an index and a row, one of my avalanche rows here, and I'm going to return some HTML. What I'm going to do with Folium is actually make markers that I can click on and they pop up details about the avalanche. So I'm going to make a bold element. I'll put in 4 placeholders here. I'll make a paragraph as well and put in a placeholder for a paragraph. Call format on that guy. And I'm going to put in my index number. I'm going to get a row that will have a year, and it will have a trigger, and it will have location, name, or route, row, accident, and rescue summary. And that will let us put in some nice information in line directly into our map. The map also needs to have a center location, so I know that the latitude and longitude that's pretty close to center will be 40.5 and negative 111.5. Now I'm going to create an instance of this Folium map, and the location will be center, and zoom start is 10, and tiles, I'm going to use a certain tiles. They're called Stamen terrain tiles. Height is going to be 700. There's my map. I need to iterate over my data frame for I row in df.iterRows, and we'll say if stir row.lat equals nan or row.lat equals 0. We'll just skip those ones. Call map simple marker method on that. Pass in row.lat, row.lawn as a list for the first attribute. Pop-up parameter equals summary, and we'll invoke summary here with RI, and our row. Okay, let's try this code and see if it works. And we'll inline our map, throw it into our Jupyter notebook. See if this worked. We have a Folium map here. This is very similar to the Google map. It's using these Stamen tiles rather than the Google tiles based on OpenStreetMap. And we can see pretty good tiles here. They've got some nice shading. Here is the Alta Ski Resort. And we can click these guys and see that row 74, 1986. Here's an avalanche here. Here's another one, 2008. Here's another one in 1976. Here's one in 2004. So a couple lines of code here allows me to quickly make a nice little map, and because I'm using the Jupyter Notebook, it's interactive and not static. Versus a Matplotlib map, I could certainly make a Matplotlib map that was static that would do similar things. That's some of the plotting that we've done. We've looked at plotting histograms. We've also looked at using maps to plot latitude and longitude using both Google Maps and this open source tool called Folium. In this section, we're going to be talking about how we made the graphics to import into a vector editor. Specifically, we're going to be creating SVG images. Most vector editors can import those and use those. So I used Inkscape to edit these, but typically graphic designers will use something like Illustrator or Sketch, and those have support for SVG import as well. So again, here's our basic infographic. We'll look at various things that we did here. We have 72 deaths over the year. We have a little plot of how many people died every year. We have a map showing the locations of the avalanches. We have a plot here showing what types of triggers triggered avalanches. We have another plot showing the elevations where the avalanches occurred. Another plot showing the slopes. Another plot showing the aspects. And aspects are the directions of the slopes. So let's look at this one, fatal avalanches over time. This is a nice little plot, and we can do this pretty easily using the Seaborn library. I'm going to import Seaborn, that's a third-party library, as SNS. That's a reference to, I believe, the West Wing. Samuel Norman Seaborn library is named after him. If I take my data frame here and I group it by the year, I can say sum reset index and pull off the year and the number killed. Let's look at what that data frame looks like. A little summary of per year what happened. Let's throw that into Seaborn. It has a function called regplot, which is a regression plot, and you pass in what you want to plot along the x. I want to plot year along x. I want to plot killed along y. And you also pass in a parameter called data, and that points to your data frame. I need to say matplotlib inline, do some cell magic here so it shows up here. And I get this nice little plot right here. Now if I want to save this as SVG, I can do that pretty easily. I need to import matplotlib, pyplot as PLT, and I need to make a figure. A figure, you can think of it as a piece of paper that you're going to plot on. So typically matplotlib makes this behind the scenes for you, but you need to get a handle to it to save. So I'm going to make the figure, then I'm going to plot. Because Seaborn is using matplotlib, it's going to plot on that figure that I just created. It's got some global state in there. Then I'm going to say fig.savefig, and I'll say temp scat.svg. To verify that that worked, I'm going to open that in a web browser. Chrome apparently knows how to understand SVGs. I can zoom in and you can see that it's not getting pixelated. Very cool. So there's basic SVGs. Let's do slightly more tweaking to it. I'm going to change the marker here. So the marker is a dot. I'm going to say marker equals x, and I'm going to do scatter KWs. Those are the keywords. These are going to get passed into matplotlib under the covers. And I'm going to say S, or the size, is going to be 100. And the color that I want to be plotted with, I'm going to use a hex string here. A4, so that should be a red color. So we just passed in those parameters. Those get passed into Matplotlib under the covers and just makes my x's a little bit bigger. Okay, the next plot that I included is this map. We saw how to do that in the previous section about plotting and using maps. Plot after that is this fatal triggers plot. Let's see how we do that. In our data frame, we have a trigger column. And if we look at the value counts of that, trigger column is categorical. So typically when we want to summarize categorical, we do value counts and we get something like that. If I take this, I can say plot.bar, and that gives me a bar plot of that. That's how I did that. You could save that as an SVG and change the color and pull off the background, and you're good to go. The next plot here is an elevation plot. Let's look at how I did that. So this is the elevation where they occurred. We have an elevation column that looks like this. And if you look at it, the type of it is an object. And it's an object because we've got values such as unknown in it. So in addition to NaN, we have unknown. So that's not good for a column that should be probably numeric. Let's change it a little bit. We'll say, I'm going to take elevation. Since it's a string, I'm going to call replace unknown with not a number, and then I'm going to cast it as a float. And with that, it should be a series at this point. I'll just do a histogram of it, and I get something like that. There's a basic histogram. Let's flip it. So in order to flip it, I say orientation equals horizontal, and I get that little guy. So I took that, saved it as an SVG, and put it on top of my little image of mountains. In this section, we've looked at how I've created a few of the graphics for this infographic using pandas and the plotting included in it. In the next section, we'll look at a few more plots and how to do those. In this section, we're going to continue looking at how the avalanche infographic was made. In particular, we'll use Matplotlib to draw a bunch of lines representing the slopes of the hills where the avalanches occurred. Then we'll see how to create a plot using polar coordinates. The next part of our infographic is the slope. This is where the avalanches occurred. This one takes slightly more work to do. I'm going to import the math library that's built into Python because I need to do some trigonometry. Also going to import the random module that's also built into Python to do some jittering. I'm going to make a function called toRadians. It's going to take degrees and it's going to convert to radians. So I return the degrees times pi over 180. Let's make an axis. An axis is a location on your figure where you're going to plot. So I'm going to say subplot, and I'm going to have one row and one column, and this is going to be the only cell in there. So that's what that 111 means. I'm going to loop over my rows in my data frame. I'm going to make some jitter here, and I'll call random.random. I'm going to subtract 0.5. Random.random returns a number between 0 and 1. I'm going to normalize it so it's around 0, and I'm going to times it by 0.2, so I scale it down a little bit. I'm jittering because a lot of the angles are the same, and in order to see some density, I'm going to jitter them a little bit to see if there's certain angles that appear more than others. Okay, I'm going to call plt.plot, and I'm going to say I'm going to plot from 0, 1, and plot to 0 math.tangent of 2 rad row slope angle plus jitter. That gives me a nice little line plot. Let's put some alpha in there so that we can see overlapping. Color equals blue and line width equals 1. And I get something like that. So pretty straightforward. Again, I'm going to start at 0, 0, and I'm going to go to 1, and then the tangent of the angle here, and that gives me how high I go up there. And if you're familiar with skiing, you'll see that most of those angles are black or double black, which is good for powder skiing and also good for avalanches, sadly. This aspects graph is a little bit harder. Aspects is categorical here. When we have categorical data, we do value counts. And we can see that coming out of there. If I want to throw this into a radial plot, I want to convert the directions to actual degrees here. I'm going to make a little mapping here. Mapping equals north, and north's going to be to 90 degrees. Northeast is going to be to 45 degrees. East is going to be 0. Southeast is going to be 315. South, 270. Southwest, 225. West will be 180 degrees. Northwest will be at 135. Just converting my categorical data to numerical values, I'm going to get my value counts here, and I'm going to pull off the items from that. So if I say value counts.items and I materialize that, I get this list of tuples. I'll just throw that into here. I'm going to call that items equals df.aspect value counts items, and I'll wrap it into a list so I can use it multiple times. Okay, I'm going to make an axis, and I'm going to say plt.subplot, 1 row, 1 column, 1 cell, and I'm going to change the projection. Projection is now polar. Rather than Cartesian, I'm going to do a polar plot, and I need some angles that I'm going to plot at, so those are going to be my thetas. X for X in items. So again, my items is that tuple of northeast to the count of things in northeast and whatnot. And I'm going to say I want to take the orientation here, that's the first guy in my tuple, I'm going to pass it into mapping. What comes out of mapping is going to be an angle, and I'm going to convert that to radians. So these are all the directions that I want to plot. And then I also have the radii, and that's how far out I want my little plots to go. So I'm going to say take x1 for x in items, and I should just be able to say bars equals ax.bar. I have my axis, I'm going to plot on it. I'm going to say plot my thetas, my radii. Okay, I got dict is not callable here because I'm calling it and I need to be doing an index operation on it. We get something that looks like that. We notice that northeast is the most common at 25, and it's not really pointing northeast, it's north-northeast. So I need to shift it a little. So what I'm going to do down here is just shift this theta a little bit. So by default, it gives me a pi slice that's 45 degrees, and it starts at the radius that I specified. If we shift it down by 22.5, we get them oriented in a better way. So that's how we make our little polar plot there of the aspects. This concludes our section about making graphics for the infographic. Again, we're just putting these into the different plotting capabilities. I saved them as an SVG and then used a vector editor to put them into an infographic. I hope you've enjoyed learning about pandas. In this series, we've talked about the series data structure and the data frame data structure. We've also looked at how to tweak data, how to plot data, and how to use data from pandas in machine learning and other analysis. In the final project, we looked at an analysis of avalanches in Utah and saw how to crawl them using Python, tweak the data, and make plots and do some analysis on that. I hope that you find pandas very useful and enjoy using it in your day-to-day work.